Okay, so let us start today's lesson. So today we'll be discussing atomic absorption spectroscopy and atomic emission spectroscopy. So if anyone has any idea about these two, they can type in the chat box. Okay, so AES and AAS. Okay, so what are these methods and why they are used? So amongst the various kinds of spectroscopy that you have learned till now, these ones are a little different. Okay, so atomic emission spectroscopy, it usually uses atoms excited from the heat of a flame to emit light. Okay, their atoms are being excited from the heat of a flame to emit light, and it's similar to that of flame spectroscopy. So the analysis can be done with a high resolution polychromator to produce emission intensity versus a wavelength spectrum, so that multiple elements can be detected simultaneously. Okay, so here just the atoms are being excited, and then a polychromator is being used to produce emission intensity versus wavelength spectrum to detect multiple elements simultaneously. Next, we have atomic absorption spectroscopy. Compared to atomic emission spectroscopy, here a flame of lower temperature is used. Okay, it is not used to excite the sample atoms like that in emission spectroscopy. So a flame of lower temperature is used so that the sample atoms would not be excited. Instead, the analyte atoms are usually excited using lamps which shine through the flame at wavelengths adjusted according to the type of analyte under study. So the amount of analyte that is present in the study sample is determined based on how much light is absorbed after passing through the flame. Okay, so the atoms are being excited using lamps, and they shine through the flame at wavelengths that are adjusted according to the type of analyte under study. And finally, in the study sample, how much amount of analyte is present, that can be determined on the basis of how much light is being absorbed after passing through the flame. Okay, there's another kind of spectroscopy here that is known as spark or arc spectroscopy. This is used for analyzing solid metallic elements or non-metallic samples which are made conductive after being ground with graphite powder, and the analysis requires passing of an electric spark through it to produce a heat that excites the atoms. And the excited atoms emit light of characteristic wavelengths, which can be detected using a monochromator. Okay, which can be detected using a monochromator. So let us discuss a few characteristics of both these types of spectroscopy. I'll share my screen. Wait. So, till now, we have learned a lot about molecular spectroscopy, where we have been learning about molecular absorption spectroscopy primarily. So, we have learned about UV visible, IR, NMR. We have even learned about fluorimetry. So, here the molecules are interacting, and within them, the vibrational, the rotational, electronic energy levels are getting perturbed. But in atomic spectroscopy, we are dealing with the interaction of electromagnetic radiation with the direct atoms. Okay, and on basis of that, we have atomic absorption spectroscopy and atomic emission spectroscopy. So what is the history of atomic absorption spectroscopy and how it was discovered? So it was first discovered by Wollaston. Okay, by Wollaston, that phenomenon was first discovered in 1802, and then much later Alan Walsh, he showed that it could be used as an analytical tool. He showed that in 1953 that absorption spectroscopy, atomic absorption spectroscopy, can be used as an analytical tool, particularly for the analysis of trace elements. And till now, more than 70 elements have been analyzed by AAS. Okay, AAS. And also, when you're doing this particular kind of spectroscopy, you do not need to resort to separation methods. Even if other elements are possible, you can determine the single element of interest. Okay, you can detect the single element of interest. And basically here you are measuring the spectroscopy measurement of unexcited atoms, that is ground state atoms. This is done by the flame method. Okay, this is done by the flame method. Now, what are the advantages of this kind of spectroscopy? It, as we have already told you, that it can detect almost more than 70 elements. Okay, the amount of sample that is used is very small. Also, it is a faster technique than other kinds of methods, and it has high sensitivity. Okay, it has high sensitivity. Also, the detection limit is 20 micrograms per ml. So this is also an indicative of sensitivity of the spectroscopy. But what are the disadvantages? Because a trained person or an expert is required for the analysis. So just we cannot go and analyze it if we are not aware of this kind of spectroscopy and the patterns. And also the instrument is quite costly. So these are the disadvantages. Now let us look at the principle in detail. In this kind of spectroscopy, the measurement of the unexcited atoms is done by the flame method. Here, the ground state atoms in gaseous state, they absorb energy and they are excited from the ground state to the excited state. Okay, they are excited from the ground state to the excited state. And when these ground state atoms are absorbing energy, they change their position from lower energy to higher energy, and the electronic transition of the valence electron is taking place. So the ground, like in we have already seen in other spectroscopies also, here also there is absorption of energy, and the excitation is taking place from the lower energy to the higher energy state, and this transition is giving rise to narrow lines. These narrow lines are called as atomic absorption spectra. Okay, this gives rise to narrow lines called as atomic absorption spectra. Now, when solution containing metal salt or metallic compound is aspirated into the flame, it suddenly undergoes vaporization. Okay, it is given to the flame and it undergoes vaporization, giving rise to gaseous atoms. And now, while some atoms they can gain energy and get excited, many number of atoms are remain in ground state and do not and are not excited. Okay, they are not excited. Now here the measurement of these kind of atoms is done by the flame method. Okay, this is done by the flame method. Now ground state atoms that are not excited, they are capable of absorbing the radiant energy at the resonance wavelength. Okay, they are capable of absorbing the radiant energy at the resonance wavelength. And when the radiation is passed through this flame, which is having the gaseous state atoms already, then the part of radiation is absorbed by these atoms. Okay, and how will you measure the extent of absorption? This will be proportional to the number of ground state atoms that are present within the flame. So now you are giving the solution, you're aspirating the solution into the flame. Some atoms are getting excited while a large number are remaining in their ground state. But these ground state atoms, they are capable of absorbing the radiant energy at their resonant wavelength. So when radiation is being passed through the flame, which is having the gaseous state atom, then the atoms are absorbing the part of radiation in proportion to the number of these ground state atoms. Now, there is a measurement of how the total amount of radiation absorbed can be given, and this is through this equation. So, if nu is the frequency absorbed by the atoms, then pi e square by mc into nf gives the total amount of radiation absorbed, where mnc are the mass of electron and velocity of light, n is the total number of atoms, F is the oscillator strength, E is equal to charge on atoms, and nu is equal to frequency absorbed by the atoms. Now, what is the advantages of AAS over FES? Okay, what is the advantages of AAS over FES? Now, what is FES? Anyone can tell me? FES stands for flame emission
emission spectrometry.
Sorry? Yes, flame emission spectrometry. So here
Right.
what happens? So in flame emission spectroscopy, the measurement of the radiation emitted by the excited atoms is measured, and it is correlated to the concentration of the sample, and it is generally used for the determination of alkali and alkaline earth metals. Okay, so wavelength of the radiation that is emitted, it is characteristic of the elements, and that is used to identify the elements, and this is through qualitative analysis. If you're going for quantitative analysis, then you can also relate the intensity of the radiation that is emitted which depends on the concentration of the element that is analyzed. Okay, so it is essentially the atomic optical emission spectroscopy technique, which uses the flame as the source of atoms excitation, very similar to that of AAS, but it is a little different. It is a little different, and that kind of emission spectroscopy is also used to identify a variety of elements that are important to the studies on enzymes and metalloproteins. Okay, so it is the flame here is mainly important, something that we have not seen in different other spectroscopies. It just the function of the flame is just to convert the samples into free ground state atoms which can be excited, potential excitable atoms. Okay, and if you have a lamp that is emitting light at a wavelength specific to the atoms and it is passed through the flame, as the light energy is absorbed, the electrons in the atoms are elevated to an excited state. Okay, but in flame emission spectroscopy, there is a disadvantage that it cannot be used for the direct determination of each and every metal atom. Okay, for example, if even if you have elements like carbon, hydrogen, and halides, they cannot be detected due to their non-radiating nature. Okay, they cannot be detected due to their non-radiating nature. Now, what is the advantages of AAS over FES, or what is the comparison? First of all, in FES, a little bit of spectral hindrance is there, which is negated in AAS, so it is not there much. Also, it is not much affected by temperature. Also, as comparison to FES, absorption AAS is very rapid technique, and even with small sample concentrations, the metals can be detected. Okay. Also, for regular kind of metals, aluminium, barium, calcium, hafnium, indium, potassium, they can be detected by FES, but there are so many kinds of heavy metals which cannot be detected by FES, and they have to resort to AAS for that. On the other hand, we have some disadvantages of AAS. As we have said earlier, already we are saying that the instrument is costly and expertise is required for analysis. Apart from that, also, there are some other disadvantages. For example, we require the sample in liquid form. Also, if it is an organic solvent, it is better over aqueous solution, thus raising the cost of the solvent also. Also, if you have some common ions, you have must have seen interference in salt analysis. Here also the spectrophotometry is also subject to interference. So there are some common anions like chloride, sulfate, carbonate, which affect the efficiency of analysis. Okay, which affect the efficiency of analysis. Now, elements which form oxide on heating, they are not effectively estimated by AAS. So, if you have many oxide forming elements, they will not be effectively estimated by AAS. Now, this is a flow chart of how the process works. Okay, so as we have said, it requires a sample to be in solution form. So, if you have a metallic sample, first we need to give it in a solution format, and that to the solution format needs to have an organic solvent. It cannot be done in an aqueous solution. So, the solution MX, suppose, is in an organic solvent. It is first converted to mist or droplets. Okay, now from the droplets, a little bit of evaporation will occur, and then the solid MX will form, almost like a eutectics, like we have seen, an intimate mixture. So a solid MX will be formed, and that will be vaporized to gaseous format. Finally, the element will be split. Okay, so M gas and X gas will be there, and these gaseous atoms will be in the ground state, and following the flame principle, they will absorb the radiation and get excited, and that will lead to the spectra. Okay, after the absorption of radiation, they will give rise to the spectra. Now, what kind of instrumentation is there? So we will be looking at different kinds of instrumentations from different materials, study materials, so that you have a holistic idea of all. So basically, we will have a radiation source. Okay, we will have a radiation source and a chopper. Some atomizers will be there. Nebulizers will be there so as to convert our sample into mists, then vapor, solid, then vapor. And then, as usual, the signals are detected by They are collected by the monochromator, then detected, amplified, and read out. So first we need a halocathode lamp, which is the source of intense narrow electromagnetic radiation. And here there are two electrodes, the anode and the cathode. The anode will be made up of tungsten, nickel, or zinc metal, while the cathode is a hollow cylinder made up of metal to be analyzed. And this entire setup is enclosed in a gas cylinder, which has a gas like argon and neon. And also at the end we will have a small window which is there for the transfer of the radiation, which is procured from here, and it is made up of quartz, silica, or glass. So here what we are doing is we are applying the high voltage from 200 to 600 volt across the electrodes. Now due to this ionization of inert gas, the inert gas is ionized because of this, and ions are produced. Now as we know, positive ions are attracted towards the negative electrode and they strike on the surface of cathode. As a result of this, atoms from the surface of the cathode are ejected, and this process is called as sputtering. Okay, this is known as sputtering. Now, these gaseous atoms, they also absorb energy by colliding with cations of inert gas. Okay, they will also collide with the cations of inert gas, and they will go to their excited state. Once they go to their excited state and return to the ground state, they will emit some kind of energy. Okay, and this radiation we can use for further analysis. So here they have just talked about the technical specifications, like how much average lifetime of the cathode lamp is there. So around for 2 years you can use the cathode lamp, and also you can also combine some more elements for the preparation of cathode. So it is possible to produce a multi-elemental halocathode lamp. The next is a copper rotating wheel. Okay, so there will be a rotating wheel which is placed in between the halocathode lamp and the flame, which is known as the chopper. So choppers का function ये होता है that it breaks the light from the cathode lamp into intermittent light. So when it is intermittent light, it will give an alternating current in the photocell. As we talked about earlier, atomizer or atomizer, it converts the sample solution into atomic vapor. And finally, the flame has some important functions. First, it has to evaporate the solvent, it has to dissociate the sample into the molecules, and to provide the ground state atoms for analysis. Okay, it provides the ground state atoms for analysis. Also, temperature of flame is always kept low because at high temperature, ionization of atoms will take place and they will not show absorption. Okay, they will not show absorption. So for atomization, first you have to the sample solution, the fuel gas and the oxidizing gas will be passed through separate inlets and they will be mixed at the top of the flame. Here you can see the top of the flame. Also, the sample solution will be converted to tiny droplets. We have already talked about this. Mist or droplets will be there, and finally they will evaporate and form a residue. And this residue will finally produce the ground state atoms. The advantages of this method is that this has high sensitivity and there is no risk of explosion. But there is also a disadvantage that it might cause clogging. There is poor reproducibility. You cannot repeat the experiment and hope for the exact same results. And also they will be dependent on the viscosity of the solution. Now, what type of burner should we? What type of burner should be used? So we all already know that these kind of gases then mixed in the mixing chamber. Okay, and we need a thorough mixing and the formation of uniform droplets need to take place. And finally, they need to have a burner. So if you're having a laminar flow or a pre-mix burner, then the droplets are very fine. Okay, the droplets are fine and the sensitivity is also high. You can repeat the experiment and hope for the exact results, and the clogging will be better. The clogging will not happen. So we can declog it easily. But the disadvantages are the mixing chamber may lead to an explosion if the experiment is not done correctly. Also, some analytical errors might creep up, because if you're having a mixed solvent and some parts are evaporating at different times or they're not evaporating as efficiently as the other parts, then there might be some errors. Okay, so you can have two kinds of burners here: total consumption burner and laminar flow or pre-mix burner. So you can see the differences between the two. So here, uh, in total consumption barrier, although there's no risk of explosion, so but still it is less sensitive and more prone to clogging, and also the droplets are not fine enough. What kind of flames are we using for the spectroscopy? We can use a fuel and oxidant mixture. Okay, you have to use one fuel and you have to use an oxidant. So you can use a mixture of acetylene and air, and this is very common. So the temperature rises from 2100 to 2400 in these kind of flames. Also acetylene with N2O and acetylene with oxygen. These are the kind of mixtures which can be used for the flame. Also, when we are planning to use the flame, then we have to see the volatilization temperature of the atom of interest and not choose it randomly. In nebulizer, we know that the sample has to be converted into a fine mist. So this is what the nebulizers do. In medicines also, we talk of nebulizers, so our inhalers. So this is kind of the same thing. It just converts that into a jet of droplets. So the liquid sample which is to be analyzed, it is sucked by a capillary with high pressure, by a gas that is moving at high velocity, and this process is also known as aspiration. Now, because of this high velocity, the sample breaks into fine droplets. Okay, the sample breaks into fine droplets and carries it to the atomization region. The next thing is monochromators. We have already known what are monochromators in the previous spectra. So they here also the prisms and the gratings are used. Okay, prisms and gratings are used, and the monochromators, they select the light from polychromatic light, and this is emitted by the HCl. And we have a prism as well, we have seen in the instrumentation, which works on the basis of refraction and is composed of glass or quartz. And the grating will be a dispersing element which has parallel equidistant grooves on highly polished metallic surface, and it can isolate a selected band of wavelength. For the detector, we have a photomultiplier tube, and it contains a photosensitive half cylinder of metal which acts as cathode. The inner surface of cathode is coated with light sensitive material like CS2O, Ag2O, and K2O, and it also consists of 9 dinodes which have coating of cesium metal and emit several electrons, and these electrons are collected by the anode. And it works on the basis of photoelectric effect. If you all know the basis of photoelectric effect, you will be able to understand this. So when light strikes on the cathode surface, it ejects the electrons due to photoelectric effect, and these electrons strike on the surface of first dynode, and ejection of 2 to 5 electrons take place. These electrons strike on surface of the second dynode, and then ejection of more electrons take place. The process is continued up to the ninth dynode. Emitted electrons are collected by the collecting electrode, and current begins to flow. This current is amplified and measured by the readout device. So the advantages is that this is very fast and we have more sensitivity as well. And finally, amplifier and readout devices have the same kind of functionality which is there in other spectroscopies as well. That is to amplify the current that is coming from the photomultiplier tube. And finally, you have a chart recorder in the form of a micro ammeter. Okay, micro ammeter. Now, as the case of UV visible and IR, we can have different types of spectrophotometer. So we have a single beam spectrophotometer or a double beam spectrophotometer as well. So in a single beam, you have two kinds of lenses, A1 and A2, okay, located between the lamp and the monochromator. Okay, so they will have two kinds of lenses. While W will be a wavelength isolation system, which can be in the form of a prism or a grating. Okay, and there can be some background correction, so they will have an optional lamp setup. Well, in a double beam spectrophotometer, we will have no blank measurements are required. So the beam of light that is coming, that will be split into two parts. So one part will be passed through the flame and the other will pass through a standard solution. So here it does not require any warm up time and detects the elements quite accurately, but the cost of the instrument is high. So how is the operation done? First, we have to see whether the zero absorbance is there or not. So we have to keep the HCl, the halocathode lamp on, and then the zero transmittance is added, is adjusted by putting the lamp off. So first you have to see the 100% transmittance is there or not, and then we have to see whether the zero transmittance is there or not. And the standard solutions of the elements to be analyzed, they are prepared first, and then the absorbance of each standard solution is measured. Finally, the calibration curve, that is the absorbance versus concentration, is plotted, and the absorbance of this unknown solution is measured, and the concentration is to find out by using the calibration curve. So how can you detect the sensitivity, and what is the sensitivity here? So here the sensitivity is defined as the analyte concentration in microgram per milliliter. Okay, it is defined as the analyte concentration in microgram per milliliter at which absorption is 1% or 0.0044 absorbance unit. Okay, it is defined as the analyte concentration in microgram per milliliter at which absorption is 1% or 0.0044 absorbance unit. So if A is the absorbance required and S is the sensitivity, we can easily find out the concentration of the standard. Okay, and finally the sensitivity will be concentration of standard into 0.0044 by the measured absorbance. So just look at the formula here. Now, detection limit. Okay, detection limit. This is defined as the concentration in microgram per milliliter, which results in the shifting of the absorbance signal to a value which is equal to the peak noise of baseline. Now, what kinds of interferences can have that we can have in atomic absorption spectroscopy? So what is interference? Anything which can cause an error. Okay, anything which can cause an error. So this can be in form of some substance that is present in the sample, any blank or standard solution, or any kind of errors which can arise due to improper functioning of the spectrophotometer. So let us have a look at that. So chemical interference, because if you have the formation of a stable compound at any point of time, then it will not undergo decomposition at the flame temperature. So suppose you have aluminum and magnesium and they have formed a thermally stable mixed oxide. So low results will be obtained for magnesium in presence of aluminum. So the chemical interference will affect the number of free atoms which are reaching to the optical path to be absorbed. So such kind of chemical interference is seen with factors like precipitation, viscosity, surface tension, and pH. Also, spectral interference can occur if the spectral lines are overlapping with each other, and the absorption and emission of an interfering species, they will either overlap or lie so close to the analyte band that resolution by the monochromata will become difficult. Okay, and but here in this case, because AAS is such a precise technique, the spectral interference is usually not detected that much. Next is ionization interference. Because we are using such high flame temperature, ionization of the atoms can take place. So if you have atoms with low ionization potential, they will undergo ionization, and the population of the ground state atom and the excited state atoms, they will be reduced. Okay, they will be reduced. So easily ionizable elements like potassium, sodium, carbon, if you are trying to overcome this effect, you can add it to the sample. Okay, you can add it to the sample, and due to these kind of easily ionizable elements, a large number of electrons will be produced, and they will suppress the ionization of analyte atoms. So this is much like your common ion effect which you have seen in salt analysis. Just think about that analogy. So the suppression of dissociation occurs because there are other common ions present. Okay, the suppression of the dissociation will occur. So here also you are adding something so that the ionization of the analyte atoms will be suppressed. Okay, the ionization of analyte atoms will be suppressed. Now the other interference which can occur is because of the background absorption. Okay, it is caused by the background absorption. Now, why does this background absorption is caused? This is caused by the absorption of the species other than the atoms at resonance wavelength. Okay, it is caused by absorption of the species other than the atoms at resonance wavelength, and this is observed because of the scattering of light. This is observed because of the scattering of light due to small unvolatilized particles which are present in the flame. Okay, so there might be some particles which are not being volatilized, and if they are present in the flame they will give you the absorption, but they will not be that of the species of interest. Okay, but this is a wavelength dependent phenomena and it can give a positive error in the analysis, so it can be minimized if we are using a background correction. In this case you can use a continuum source in form of a deuterium arc and you can minimize such kind of background absorption. Now, what are the applications of atomic absorption spectroscopy? So, well, in qualitative analysis, we are usually using different kinds of halocathode lab for different elements, and it is a very powerful technique for the quantitative analysis of trace elements. So here what we are doing, we have already said how we adjusted the transmittance first, and then the standard solutions are prepared, and the absorption of each standard solution is measured and the calibration curve is plotted. So this is how the absorption versus concentration is looking like. So if you have absorbance of the unknown and you can find the slope and the concentration, then you can find by using the calibration curve, you can find the absorbance of a unknown solution. Okay, you can find the absorbance of an unknown solution by using the calibration curve. Similarly, you can use this kind of spectroscopy for simultaneous multi-component analysis. So by using this multi-component lamp, elements like zinc, cadmium, zinc, calcium, iron, manganese, copper, magnesium can be detected in the spectral region between 232 to 328 nanometers. It can be used for analysis of biological material and food material as well. Okay, it can be used for analysis of biological material and food material. Now, trace metals from biological system, nickel from vegetable oil, copper from beer, sodium and potassium from blood serum, they can also be analyzed by AAS, and it is also used to find out impurities present in food material. Now, how can you determine lead in petrol? This is also a kind of spectroscopy which can help you here. So you all know of anti-knocking agents used in petrol. This is to increase the fuel's octane rating. Okay, this is an additive that is used for reducing the engine knocking property and to increase the fuel's octane rating. So tetraethyl lead and tetramethyl lead, we have two anti-knocking agents used in petrol. This kind of spectroscopy we also use to find out impurities in our food. I hope you can just find out the guidelines through which this kind of spectroscopy is being used currently in food impurity offices, like those who are detecting this, food control officers. If this kind of spectroscopy is being used or not, you can find out. Now, let us just take an example of how we are going to determine lead in petrol. So, we can have two methods, direct and indirect. If you're measuring it directly, then as we have already mentioned, you first measure the absorbance of the standard solution and a sample solution in at the wavelength 283.3. You are going to plot the calibration curve and you can determine the concentration of lead in petrol. But if you're not going for this, first you take standard solutions of lead containing different kinds of concentration like 50, 25, 10 and 5, and you prepare them using deionized water. The absorbance records at 283.3, and then you are treating the unknown sample with bromine, and lead is being converted to PbBr2. This is then extracted in dilute HNO3 and the absorbance is recorded. Okay, and then the absorbance is recorded. I want you to take down this equation. How can you measure the concentration? You can measure the concentration using this kind of equation. So you can just take down this equation in your copies. Okay, I think you have already taken down this equation. So if you are asked a question regarding this, if you're asked to solve a numerical, I'm sure you will be able to do this. Okay, so this is again a schematic diagram of what is happening during an AAS. Okay, and these are the different kinds of setups that are there. We have already discussed the general scheme of the instrumentation, and different just types of instruments are being used. Like if we are discussing monochromator in some kind of instruments, so Zerny Turner kind of a monochromator is being used. So you can see them here. Now what we have already discussed some of the kinds of applications, so do find out some other applications that are there, because this kind of spectroscopy AAS, it finds wide applications in fields that vary from mining to pharmaceuticals, environmental control, and agriculture. And most of these heavy metals are toxic, and they should be avoided as far as possible. So if we are using antibiotics also, we must have a quality control process to ensure that the drug is free from catalysts like palladium, platinum, okay, used to make them, and this can be performed by an AAS. Similarly, food, health supplement industries, they also make use of absorption spectroscopy to ensure that the products are safe for consumption. And also in mining, a lot of focus is on the recovery of precious metals like gold from old mine heaps. And with the help of this kind of spectroscopy, the amount of gold can be quantified to determine whether it would be profitable to extract it or not. The analysis of drinking water is also probably one of the most important applications of AAS, especially in places where the environment is not properly cared for. So, if we were to sum up the advantages and limitations of AAS, we would again go back to what we've already read, that it is easy to operate, it has high accuracy, it is mostly free from inter-element interference, and has wide applications across so many industries, and also has high sensitivity. But the limitations, if we are seeing that the equipment is expensive, the sample might be destroyed, because of course the sample is going through a vaporization phase, so it will be destroyed. And it will be more geared towards analysis of liquids, because the sample to be submitted has to be in the liquid state. Also, the solvents that are being used, they have to be organic. And it also requires a high level of expertise to analyze a spectra like this. Okay, analyze a spectra like this. So I'm just going to show you one kind of diagram, how the spectra looks like, and what they have like used in this kind of spectra. Just 1 second. So as you can see here, tin, iron, and cadmium detection in a food sample. So this was recently coming up in a science news, that AAS has been used to find out the detection of these kind of elements in the food sample. So as we have mentioned, this is the this is the kind of spectra that happens, and it is the integrated absorbance versus wavelength. It is okay. It is the integrated absorbance versus wavelength. So such kind of spectra are obtained in AAS. Now we have talked briefly about flame emission spectroscopy, And we are also going to, since we are more familiar with the kind of patterns that AAS has, we are also going to compare that with FES now, and we are going to discuss the FES in detail as well. Just one moment. So we have talked a little bit about this when we started AAS. So essentially, it is the measurement of the radiation that is emitted by the excited atoms, and it is related to the concentration of the sample used for the determination of alkali and alkaline earth metals, because they are giving a characteristic color to the flame. We all know through the different flame tests that we have performed during our graduation days that different flames can give different colors on the basis of which alkali or alkaline earth metals are being used. Now, for qualitative analysis, if we are seeing the flame color and we are deciding something, then that is your qualitative analysis. But if you are seeing the intensity of emission and it is relating to the concentration, then you can use this for the quantitative analysis. And this is mainly used in hospitals to measure the level of sodium and potassium in body fluid and tissues. So what is the principle? Here also very similar principle will be there, that you're introducing the salt solution in form of a mist. It evaporates from the solid forms vaporization, and then they dissociate into neutral gaseous atoms. And here what is happening? There is absorption. During the thermal energy, atoms are excited to the higher energy field. As soon as they go away, they're emitting some radiation. Now these emitted wavelengths are specific for specific elements, and that is how we detect these elements. So we already know that if we are seeing about some emitted light, then H nu can be the difference of energy between the ground state and the excited state, where H nu will be the frequency of emitted light, and E2 and E1 will be the excited and ground state respectively. So Hc by lambda will be equal to E2 minus E1, and from the wavelength value element present in the sample, we can find that out. Now here is the Boltzmann distribution, Boltzmann equation. So this is a very common method of seeing what population of atoms are present in the excited state as relative to the ground state. So if n is a number of atoms in the ground state and n star is there in the excited state, and we can take a as any constant, sometimes a constant is also ignored, then ea will be the difference in energy of the two levels, that will be difference in energy, and it will be the excitation energy, while K will be the Boltzmann constant and T will be the temperature of the flame in kelvins. At higher temperature, the number of excited atoms is also more. So, number of excited state atoms also depends on the flame temperature, that is T. Okay, it is T. Now we have seen the types of flames that have been used in AAS. Now here, since we are seeing that the number of excited state atoms is dependent on the flame temperature, if we are increasing the flame temperature, number of atoms in the excited state is also increasing. So we had seen only a limited number of flames that can be used in AAS, and here we are finding out that in flame emission spectroscopy you can use more types and more combinations of flames. There only we were using acetylene air, acetylene O2, acetylene N2O, and here we are being able to use hydrogen air, oxygen, methane air combinations, methane oxygen, propane air, propane oxygen combinations, butane air, butane oxygen combinations. And this selection of the flame, it will depend on the volatilization temperature of the atom of interest, as we've already seen in AAS. Now here, this is again a flow chart of how the events occur. It is very similar to AAS. Okay. But here just the difference is, after the formation of the solid and the dissociation is occurring, excited states are they're going to the excited state, and then they're again emitting something. Okay, they're emitting the radiation and then they're returning to the ground state. The excited state are returning to the ground state. This is an additional step which was not there in AAS. So this is another overview of the process. Just have a look at it. Okay. So what is the advantage of FES again? Same that of AAS, that it is faster, it is more accurate, particularly for alkali and alkaline earth metal is good and it is easier also. But the disadvantages which we have already seen in case of AAS when we were comparing is that only limited number of elements can be analyzed, and also the concentration, mainly the concentration that is required for analysis should be also high, whereas in case of AAS very small amount of sample was required. But one common disadvantage for both AAS and FES is that the sample in liquid form is necessary, and that is possibility of spectral interference, and this is particularly more for FES than AAS. So we have talked about how the flame is very necessary in both these kinds of spectroscopy, and here we are going to see the factors that can affect the intensity of the flame. First is that, of course, for me, the top choice will be the temperature of the flame because it is affecting how many excited state atoms are there. Then, of course, the flame composition, which kind of flame is being used, the solvent that is being used for dissolution, concentration of the analyte, also what is the rate of formation of the excited atoms in flame, and how are you introducing the sample in the flame. So this is all the factors that are affecting the intensity of the flame. And it is to be noted that for alkaline earth metals we can use a high temperature flame and it will be preferred. But if you have alkali metals, they can easily undergo ionization, so high temperature will not be required for analysis of these elements. Okay, so high temperature will not be required for analysis of these elements. Now, flame emission spectroscopy. So we have instrumentation like this. Okay, this is very similar to what we have already talked about in AAS. So this is the general scheme, and I'm not going to go into details, but rather what kind of burner and what kind of the instrumentation is there, I will focus on that. So here also we find the total consumption burner is there, like we saw in AAS. Then a laminar flow burner is also there. Again, we have seen this. The type of burner here differs a little. Here we also have an additional type of burner like the Mecker burner, and it can use natural gas as fuel and air as oxidant, but the flame temperature is low, so it can be used only for easily ionizable elements. Particularly for alkali metals it is used. Also, it produces such low temperature and the flame is also not homogeneous, so it is at a disadvantage here. Now the mirror which is used here, this is the most important component in FES, and it is placed behind the flame because it creates inverted image of the flame of the equal size at the location of the flame. And for this we are using a concave mirror, and the slits, that is the entrance and the exit slits, they are used to control incoming and outgoing radiation. We have already talked how monochromators which are being used in this kind of spectroscopy is prism or grating, so we will not go into this. The detectors here are different. There it was a photo multiplier. Here we have a different, slightly different kind of a phototube, which consists of an anode and a light sensitive cathode, and they are placed in an evacuated glass or quartz bulb, and a potential difference is applied across the electrodes, and when radiation is striking on the surface of the cathode, we have a photoelectric effect and the ejected electrons are flowing. Here, the inner surface of the cathode is coated with light sensitive material like CS2O, Ag2O, and K2O. And finally, when the electrons are being produced, they are connected by the collecting electrode. This is also quite similar. In the readout device here, we were seeing in the AS how chart recorders were there and ammeters were there. Here, we are using a galvanometer. Okay, here we are using a galvanometer. So what is a kind of general thing that we are doing? That we are dissolving the sample in the solvent, and then they're aspirated to the flame. Ground state atoms are produced. They go to the excited state. They return to the ground state by emitting radiation. Now this emitted radiation that is passed to the monochromator strikes on the detector, and finally the detector response is amplified and given to the readout device. Now, like we had seen in AAS, different kinds of interference are there. It's the same kind of thing, but here the spectral interference is very, very common in FES, which was not there in AS. It was kind of a one-off thing, but here in FES, it's a very common thing because the iron line, they are overlapping with the copper line. Sometimes the aluminum line is overlapping with the vanadium line. So it gets very difficult for the FES to detect which line is which. Okay, so the resolution by the monochromator sometimes becomes difficult, particularly when the flame temperature is high, because at that temperature, more number of spectral lines will be produced. Similarly, ionization interference, because the ionization energy of these elements is low and it is used for the analysis of alkaline earth metals, the ionization interference is also very common in FES. Okay, and to overcome this, we are using oxidizable elements, similarly, which we have seen already in AAS. The same kind of chemical interference is there if we are forming mixed oxides. The same kind of problems are formed and the chemical interference is there. There is another kind of two errors which is not there in AAS but is there in FES, that is the anion error and the cation interference. The anions interfere as components of salt and acid, and chloride and sulfate, they can cause this kind of interference. And we also have some cation interferences like from sodium and potassium, and they might decrease the signal intensity. The background absorption interference is the same as AAS, so I'm not repeating this one. Now, quantitative analysis, how will we do? We can do this by three methods: the standard addition method, the internal standard method, and the calibration curve method. Calibration curve method, we've also known how it is done. Just we'll go through briefly with the standard addition ones. So here we are plotting a signal against the concentration of the solutions. The concentration of the solution is taken in x-axis, okay, and the signal intensity on the y-axis. So a series of solution containing fixed amount of unknown x and different amount of standard solutions is prepared, like x plus a, x plus 2a, x plus 3a, x plus 4a, and the signal intensity of each of these solutions, it is measured, and a plot of signal versus concentration is now plotted. Now, if we are having some kind of unknown solution, that is x, we can determine how that is there with the intersection of the curve with the concentration axis. So we can just plot and connect all the points that are there, and wherever it crosses the concentrated axis, we can see the concentration of the unknown solution. Similarly, another kind of method is the internal standard method. Here we are preparing a series of standard solutions and a known amount of internal standard is added. The signal intensities of all standard solutions which are having internal standard are measured, and we are measuring the signal intensity as well. The graph of ratio of the signal intensity versus concentration is plotted, and concentration of the unknown solution is then determined. And here we have already seen, as in the previous example of AAS, how the calibration curve is here. The only difference here is the emission intensity is being recorded. Okay, instead of the absorbance, we are seeing the emission intensity and we are plotting it against concentration. So if we are connecting the dots by some kinds of standard solutions we are preparing, and we are seeing the emission intensity and connecting the dots, if we are having some unknown solution of unknown concentration also, we can find out using the extrapolation method. Okay, we can find out by extrapolation method. So emission spectroscopy, like that of the other flame spectroscopy, that is atomic absorption spectroscopy, more than one element can be done. Also, soil and water analysis, this is very useful for because this can be analyzed by FES. It can even decide what kind of fertilizer is required. It can help in narrowing down the choices, because the iron content of the soil, the water, calcium, potassium, sodium, magnesium, everything can be analyzed by FES. Now, this technique is also very useful in analysis of food products. Fresh milk can be studied for the nutritional value, particularly fruit juices, soft drinks, alcoholic beverages, buttermilk, everything can be analyzed by FES. And as it is used for sodium and alkali and alkali earth metals, the body fluid potassium and sodium level, is particularly important for maintenance of body balance, and this can be analyzed by FES. And it is also used in variety of other fields like analysis of geological materials such as minerals, ores, clay, petroleum, and also we can carry out the wastewater analysis from the industry. How do we prepare the standard solutions? This is very easy, and being analytical chemistry students, we already know how to do that. We can just dissolve a particular amount of the salt in deionized water in the graduated flask. Okay, and we can get the solution diluted to have different kinds of concentrations. Okay, we can easily prepare the standard solutions in lab. I'm going to stop here and for a break. Okay, in 10-15 minutes, we are going to resume again, and then we will be discussing some questions. In the meantime, I'll also be forwarding some links, and a few of you, please give me your email IDs in the chat box so that I can forward some materials to you regarding this class and previous classes as well. So please give me some email ID so that I can forward the presentations or some kind of materials to you as well. So we will again come back in 15 minutes. So you can take a washroom or a water break, and we will come back. Okay, I think we can come back now. Just get ready. We will also discuss a small portion of atomic fluorescence spectroscopy. I'll just introduce it. But before that, let us discuss some questions that have come from this portion. As I say, you can note them down in short. Okay. We will also, in the subsequent classes, we will also be discussing some questions which have come in the other spectroscopies like IRUV. So we missed out on some of them. So in 2011, it had come like a very general question because the monochromators are found everywhere. So they had asked what are monochromators and describe how a grating monochromator works. So it's a very general kind of a question. So anyone can answer that in the question paper. You can in fact tell them about different kinds of spectroscopies and how the grating monochromator helps select a particular band of wavelength. So the construction of a monochromator you should be aware of. They have also asked how are these better than color filters because they are very selective. Okay, they are very selective. Next, it was asked. This is again very general. What is meant by photo emission? Okay, photo emission. What is meant by photo emission? Next, we have just discussed this. Describe the structure of a pre-mixed or laminar flow flame. Describe the structure of a pre-mixed or laminar flow flame, clearly indicating different regions. Okay, this one you will be able to answer. Okay, describe the structure of a pre-mixed or laminar flow flame, clearly indicating different regions. Then very direct question, major advantages of flame photometry. Okay, major advantages of flame photometry. Then principle of introduction of sample in AAS. Principle of introduction of sample in AAS. Then how is a double beam atomic absorption spectrophotometer better than a single beam spectrophotometer? How is a double beam atomic absorption spectrophotometer better than single beam spectrophotometer? Then very direct question again. Explain principle of atomic absorption spectrophotometry. Explain principle of atomic absorption spectrophotometry. This is a specific question. What is the principle of calibration plot method? What is the principle of calibration plot method in atomic absorption spectrophotometry? What is the principle of calibration plot method we have just discussed for atomic absorption spectrophotometry? Limitations of flame photometry. Again, this kind of question has come. So advantages and limitations, be very thorough with them. Limitations of flame photometry. So this is all for your 2011. When we come to 2012, I think. 2012. Again, processes in flame photometric analysis. Processes in flame photometric analysis. Applications of flame photometry. Applications of flame photometry. Quantitative applications of flame photometry. quantitative applications of flame photometry. I hope you are noting all this down. Then some more questions. Okay, now you remember in I had told you how the pattern of questions is, that total 5 questions you have to answer, where question number 1 will be compulsory, and in question number 1 you can have 6 sub questions, out of which you have to choose 5 and write, and these 5 will be of 3 marks each. So for 3 marks each, see the kind of question which is coming here. Define nebulizer, monochromator and line spectrum. Define nebulizer, monochromator and line spectrum. We have already discussed nebulizer. Okay, and you can also write about monochromator and line spectrum. Next you write, this is just we have discussed very extensively, what types of interferences are possible in flame photometric analysis. What types of interferences are possible in flame photometric analysis? This is a question for 5 marks. Okay, this is a question of 5 marks. What types of interferences are possible in flame photometric analysis? Then in 2013, 2013, not much was given. Yes, draw schematic diagram for the number of processes which an analyte undergoes when placed in the flame. Okay, we have already shown you several schematic diagrams, like the sample is undergoing mist and droplets, then it is undergoing, that is becoming a solid, then vaporization. Okay, all of that is happening, so that will be your schematic diagram. So you write, in flame photometry, in flame photometry, analyte undergoes analyte undergoes a number of processes. In flame photometry, analyte undergoes a number of processes when placed in the flame. In flame photometry, the analyte undergoes a number of processes when placed in the flame. Draw a schematic diagram. Draw a schematic diagram illustrating these processes. Draw a schematic diagram illustrating these processes. Okay, now again this kind of question is coming for interferences. Again it is coming like 2012 it came, 2013 it came. Spectral interferences. Okay, atomic spectrum is accompanied by a number of spectral interferences. State different types of spectral interferences which is observed in flame photometry. Already this question has come, so you can just focus on this question again and again. Then operating principle of a photomultiplier tube. Operating principle of a photomultiplier tube. See what kind of small questions are coming for 3 marks. Okay, what is meant by total combustion burner? So all the burners you learn, small details about the photomultiplier tube also you learn. Okay, again it has come in another question paper. Briefly describe types of reaction taking place when analyte is placed in flame for flame photometry. Again you will draw the schematic diagram and explain. Okay, you can draw the schematic diagram and explain. So a little bit of question has been twisted, so you can easily answer that. Applications, qualitative and quantitative application of atomic spectroscopy. Qualitative and quantitative. Merits and limitations of flame photometry. Again, this kind of question is coming in 2014. Merits and limitations of flame photometry. Why is flame photometry called atomic flame emission spectrophotometry? Why is flame photometry called atomic flame emission spectrophotometry? See, again, third time the question has been repeated. What kind of chemical interferences are found in flame photometry? What kind of chemical interference? So this one question was write all the interferences. Another question came, write spectral interferences. Then another question is coming, write chemical interferences. So you should be thorough with this question. Merits and limitations of flame photometry. Again, third time repeated in another question paper. Spectral interferences again repeated. Fifth time we are seeing the spectral interferences. This was in December of 2014. Then, okay. Why simultaneous multi-elemental determination? Why simultaneous multi-elemental determination is easier in atomic spectroscopy? Is easier in atomic spectroscopy. For the sixth time again in 2015, merits and limitations of flame photometry came. 5 marks. Again, it has been repeated. Wherever it is repeated in the question that you are noting down, give a tick mark. So you know that that question is coming again and again. Okay, this one is a different question. What precautions should be observed while preparing samples for AAS? What precautions should be observed while preparing samples for AAS? Give importance to the kind of solvent. Okay, solvent, you include that point that there should be liquid solution, the solvent should be organic solvent. Okay, amongst other kinds of precautions like impurity should not be there. Okay, what precaution should be observed while preparing samples for AAS? Applications of flame photometry. See, again and again, these kind of questions are there. Applications of flame photometry, advantages of atomic absorption spectrometry and atomic emission spectrometry, advantages of AES and AAS, applications of flame photometry. Also, again, that question is repeated. Why is double beam atomic absorption spectrometer better than single beam spectrometer? Already it has been asked once. It is again repeated. Again, for the sixth or seventh time, interferences in atomic absorption spectrophotometry. So you're seeing how important this question is. Interferences in atomic absorption spectrophotometry. Okay, now trick question has been asked. Why is atomic absorption spectrometry not an ideal method for determination of alkali metals? Why is atomic absorption spectrometry not an ideal method for determination of alkali metals? Which method would you recommend for the determination of these elements? Very simple. If you know about flame emission spectra, you can easily write flame emission spectroscopy. So you can write that AS is not preferable, but FES instead is preferable. Okay. Next, what is the role of atomizer in flame photometry? What is the role of atomizer in flame photometry? What is the role of atomizer in flame photometry? Define nebulization. Define nebulization. Define nebulization. Explain the fate of sample in a flame. Explain the fate of sample in a flame. Explain the fate of sample in a flame. And again, for the eighth time, our favorite question, various types of interferences in flame photometry. Explain briefly. Various types of interferences in flame photometry. Explain briefly. Explain the basic principle of atomic absorption spectrophotometry. Explain the basic principle of atomic absorption spectrophotometry. Give relation between concentration and absorption. Give relationship between concentration and absorption. Again, spectral interferences has been asked. So you just give a tick mark wherever you've written. Okay, now again one specific question has come. Draw a labeled sketch of hollow cathode lamp. Draw a labeled sketch of hollow cathode lamp and explain use in AAS. We have just discussed. Draw a labeled sketch of hollow cathode lamp and explain use in AAS. Next question you write, define a flame. Define a flame. Define a flame. Explain how different combinations of fuel gases and oxidants explain how different combinations of fuel gases and oxidants can give different flame temperatures. Explain how different combination of fuel gases and oxidants can give different flame temperatures. You can refer to both AAS and FES when you're explaining this, saying how acetylene oxygen, acetylene N2O, okay, this can give different flame temperatures. And in case of FES, how methane O2, propane O2, butane, all of this can be giving different flame temperatures. So remember a few, because this question has come, high chances that it will again be coming. Again, various types of interferences in atomic absorption spectrophotometry. Favorite question. Okay, another similar question. Briefly describe the flames commonly used in flame photometry. Briefly describe the flames commonly used in flame photometry. Okay, what are the most important reactions that occur in a flame during flame photometry? What are the most important reactions that occur in the flame during flame photometry? Again, quantitative applications of flame photometry with suitable examples. Quantitative applications of flame photometry with suitable examples. Then again, questions repeated. Define nebulization and various processes that occur in flame. Define nebulization and various processes that occur in flame. Different methods used for quantitative determination using AAS. Different methods used for quantitative determination using AAS. And again, very easy. Explain basic principle of atomic spectroscopic methods. Basic principles they're asking. And they're also asking schematic representation. They're also asking for schematic representation.
Excuse me, ma'am.
Yes.
Different method for AS means direct and indirect both methods we have to mention.
Which one?
Just
Atomic spectroscopic methods. Just you have to give the basic principle of the spectroscopy. Okay, you have to give the basics principle, you have to give the both the direct and the indirect methods, and then you give the schematic representation.
okay.
Okay. Same kind of question is also there. Explain reactions that occur in the flame considering a molecule mx. We have already seen how considering a molecule mx we can show what are the reactions. Explain internal standard method used in flame photometric determination. Explain internal standard method used in flame photometric determination. Again, they have asked about interferences as well. Interferences, again, it has been repeated. Give a tick mark there. Merits and limitations of flame photometry repeated. This we have come to 2019 now. In 2019 also they are asking, explain various processes that occur in the flame when solution containing analyte is aspirated into it. Just a change in wording, but the same thing. Various processes that occur in flame. Then this is another question which you can write down. Different types of atomizer burners used in flame photometry. They are now asking about burners. Different types of atomizer burners used in flame photometry. Compare their performance. Compare their performance. Then again, they have asked about principle of atomic absorption spectrophotometry. What is the importance of calibration plot in AAS? What is the importance of calibration plot in AAS? So these kind of questions have also been repeated in 2020. Quantitative analysis by flame photometry, important reactions when analyte is put into flame. Okay, differentiate between FES and AAS. Okay, essential component of typical atomic absorption spectrophotometer, draw schematic diagram. This also you can do. Essential components of typical atomic absorption spectrophotometer, draw a schematic AAS. Role of organic solvents in AAS. Role of organic solvents in AAS. What are the two types of atomic absorption spectrometer? Which one of these is better and why? Same kind of question, language is different. Draw a schematic sketch of any one of this. Okay. Again, basic principle of AAS. Then in 21 also interferences came. Okay. What are the two types of sources of radiation used in AAS? Explain in brief. Write this. What are the two types of sources of radiation used in AAS? Explain in brief. Now, very specific questions are now being asked regarding this particular portion. Discuss role of nebulizer in flame photometry, giving a schematic illustration. Nebulization is coming again, but in a more detailed way. Describe internal standard methods of calibration for flame photometry. Internal standard methods of calibration. Same thing, question will be a little twisted. Reactions occurring when analyte is introduced into the flame. Again, repeated. 5 marks questions, these are coming. And then what is hollow cathode lamp? Describe all components with help of schematic diagram. This is also repeated. Hollow cathode lamp. Various kinds of interferences, again coming back 2021, 2022. Then hollow cathode lamp has been repeated again. Neat diagram, explain its working. Okay. Applications of AAS. explain reactions in flames, applications of AAS in area of environmental analysis, right? Applications of AAS in area of environmental analysis, explain water atomizers, explain water atomizers. Again, these kind of questions are repeated. Role of organic solvents, okay, role of an organic solvents. So till almost 2022, we are updated regarding this portion. I took special care for this particular portion because usually we all have read about IR, UV, mass, NMR. We have some kind of idea and we'll be able to solve the questions. Still, we'll be solving some questions from the previous year question papers next week after we are completing this portion. So we will be discussing more questions. But for the last 10 years, some questions are being repeated again and again, just a little bit of sometimes they're asking more details, sometimes they're asking more components, explain the working, explain the diagrams. So this kind of things are there. Hmm. So I'll just quickly walk you through atomic fluorescence spectroscopy, AFS. Regarding this, also questions are being asked. So we will not ignore this one. So just quickly, I will walk you through the presentation. It's not much. Okay, so here this is also a kind of atomic spectroscopy, but here also we are measuring the emission, and here the emission is in fluorescent signal. Okay, here the emission is in form of fluorescent signal, and it is used to study the electronic structure of atoms and to make quantitative measurements. Okay, now, what is the principle of AFS? Same kind of principle is there. Radiation is being absorbed, going to the excited state, coming back to electronic state. Here they are emitting a photon. Okay, here they're emitting a photon and we're measuring the intensity of the emitted radiation. And here there are three main types of the fluorescence, the most sensitive of which is the resonance fluorescence. We have all known about the Jablonski diagram. Here, this is a different kind of fluorescence that we are seeing. Same kind of principle though. Okay, resonance fluorescence, direct line fluorescence, and stepwise fluorescence. Okay, stepwise. So resonance is like it got excited and then it came back to the ground state. Same, like it is a very direct kind of resonance. The fluorescence is happening here in direct line fluorescence. It is getting excited, then it is stepping back into some an intermediate state, and then radiation-less transition is occurring. And in stepwise fluorescence, first it is getting excited, then it comes back to an intermediate state through a radiation-less transition, and finally it is giving a stepwise transition. So here again, you need a holocathode lamp, monochromators, photomultipliers. So we are not going into the instrumentation because it is similar to that of AAS. So if you learn about the AAS also, you can just do the schematic diagram of AFS. Okay, so in one study material, you can find everything. You will be able to do it. Types of interference of AFS also, same kind of thing. You will learn more about matrix effects, chemical reactions, light source drift. Okay, so here they do not much affect the accuracy of the analysis. Okay, because if you are having spectral interference, that is very minimized in AFS. Okay, that is very much minimized in AFS. The only things which will cause effects are chemical reactions and light sources. And applications for mainly determination of hydride forming elements like selenium, okay, antimony, mercury. Okay, and it has wide linear calibration range, which has a wide range of applications as well. So environmental, biological, food samples is there. So different other kinds of absorption spectroscopy are usually more popular, but in gas chromatographic techniques they are used as detectors. So they are very specific kind of spectrophotometry. So this is how a spectrophotometer looks like in real life for the AFS system. Okay, we will be studying more about this one, and then we will also take up a little bit of AES, atomic emission spectroscopy. We will see how is it different from the AAS that we have learned today, a little about that. Then in the subsequent classes we'll go to photoelectron spectroscopy and X-ray spectroscopy. I will be sharing some materials with only a few of you. So many email IDs maybe I cannot send, but if I send to two or three, then please forward them in the group that you have. Okay. I will try and send to as many people as I can. Okay. So thank you. We will wrap up this session today here. And in the next classes, I am hoping to discuss as many questions as possible so that you get an idea of how to prepare yourself. Okay. So thank you so much.
Okay,
Good night.
thank you. Good
Good
night.
night.